Okay. Can you confirm that you can see the blackboard, the whiteboard?
Yes.
Okay, thank you. So, okay, the last thing we saw last time was a concept that is okay. I understand it's a little tricky. I had a couple of questions in the email regarding the difference between a global and mechanism. Okay, we saw this an example of this here. This was a global mechanism, which means that it's not representative of actual collisions that take place. Okay, it is not. Okay, it is. You have to think of it as a sort of a very sketchy or very approximate summary of what is actually going on at the molecular level. Okay, you have a lot of those global or reduced mechanisms, and we will later on we will talk extensively about what that means. Okay, in especially in reactive. There's some latecomers. Especially in reactive computational fluid dynamics. Okay, so the actual simulation of reactive flow with reactions, which is one of, I guess, the most computationally intensive activities that you can actually do with a computer. Obviously, we're not talking about your PC, we're talking about supercomputers. So with tens, if not hundreds of thousands of processors. Well, clearly the chemical mechanisms, okay, that we will see later on that exist for even the simplest hydrocarbon fuels, they're really, at this point, too complicated and too computationally intensive to use. That's why usually you resort to some sort of reduced or global mechanisms, okay, of some kind. Now, we'll see how they're constructed. In this particular example, here, we just saw that this was a stoichiometric sum, if you will, or of two sub-processes, which are actual elementary steps, okay? When I use the word elementary, I'm actually referring to the actual molecular collision, okay, between molecules. Now, of course, these are two distinct problems. I mean, this one with the little circle and these two with, let's say, the square here, 1 and 2. These are distinct problems in the sense that I can write down, okay, ordinary differential equations for these species using the global mechanism, or I can write down ordinary differential equations for these species using the actual detailed mechanism or the elementary mechanism, okay? And I will get two different systems. In particular, I will get two systems that have different timescales, okay? And that is what is really the important message. So in some sense, the global mechanism is really hiding, okay, is more simple and is really hiding the sub-processes. And so what it, in terms of time scales, what it really does tell you is that it will inherit what is called the rate limiting, okay, time scale. So you have to think of this. I made the example of the slow car, the Cinquecento, driving in a row of very fast Ferraris or something. And of course, the whole line will move as fast as the slowest car. You can think of this as, for example, a series of containers, okay, carrying some liquid, okay, with different mass flows, okay, in series, okay, and clearly, depending on the size of the little hole here, you can have some sort of mass flow. But you can see here, if there is a rate limiting case or a rate limiting container here, okay, the final mass flow of this liquid falling from top to bottom will be as big or as large as the smallest or rate limiting step. Okay, so it's a series of elementary steps, 1, 2, 3, but the global, okay, system is like a black box here, which is hiding those systems in some sense, okay, and we'll only see this kind of resulting timescale. If I look into the black box clearly, I will also notice that there is an initial kind of very, very fast timescale related to the fact that this container has a very large hole and will let a lot of mass flow through. Okay, so this is a very sort of simplified version of the concept. Okay, but we'll take a rigorous path and analyze this mathematically. Okay. So the concept of reduced systems and the concept of timescales is something that we will be rather involved in what follows. Okay, but I want it to be clear that these are not equal; they're not equivalent. They will tell you two different things. Okay, and the resulting ordinary differential equation that you can write are in fact different. Okay, good. Okay, I think we can skip this. The units we've done. Okay. Another fact that we can look into is the concept of pressure-dependent reactions. You can hear me, right?
Yes, Professor.
Okay. This will, in some sense, complexify things even further, okay? What have we seen so far? Let me just recap here very briefly. Well, we've seen that for an elementary reaction, okay, the reaction rate was something like a constant times the product of the concentrations, if you remember, okay, to the power of the stoichiometric coefficient. I've always, at this point, considered only irreversible reactions, such as these, okay? Later on, I will also consider the inverse process. This is for elementary, okay? Depending on these exponents, you can have a first order, second order, or third order reaction. And typically, we've seen that the reaction rate, okay, if you remember from collision theory, we will look into this even further, but for the time being, remember, there was essentially a frequency factor, okay? So for example, for a reaction of this kind, okay, there was a frequency factor times the product of the concentrations A, B, right? If you remember. Indeed, this was this unit here, so the product of concentrations time this function, which is essentially a function of the kinetic energy, okay, of the molecules, okay, this was a measure of the total collision frequency, okay, and the rate of reaction is not equal to the total collision frequency because, well, as you know, the distribution, okay, of kinetic energy between the molecules is, you can think of it as a Gaussian distribution. And not all of the collisions will be energetic enough. So you have to multiply by a factor, okay? Don't worry if you don't remember this, we'll do it again, which is the fraction, okay, of molecules actually possessing an energy which is big enough, okay, for the reaction to actually take place, okay? So this is the fraction of the total collisions that have enough kinetic energy, okay? So we expressed a form of the reaction rate which is generally known as the Arrhenius, okay, form. Okay, Svante Arrhenius was this Swedish scientist, okay, who first came up with this expression. So generally speaking, if I have an elementary reaction, okay, that I can write down, okay, I can immediately write down the form of the reaction rate, because the reaction constant K will be essentially this ZT times the exponent, and then this is the product here, this term here, the product of the concentrations, okay? And I can write it down. But unfortunately, it's not always that simple, okay? As you can see here, essentially there is only a dependence K, okay, has a dependence on temperature through this, essentially this term here, the frequency factor, and the exponential here, which is the fraction of molecules having enough energy, an energy which is bigger than the activation, equal or bigger than the activation energy, okay? Again, don't worry, I'm just giving you sort of a preview of what we're going to do later on, okay? We're going to get back to the Arrhenius form, okay? So it's only a function of temperature, which makes sense, right? A reaction takes place because there is a collision that is energetic enough, okay, between two molecules. And so it's very clear that the rate at which this progresses macroscopically, okay, will have to do with the kinetic energy of the individual molecules, okay? However, that's not totally true. Pressure does have a role, and I'll give you two examples. If we talk about pressure-dependent reactions, in effect, we are not talking about the actual Arrhenius form. So some people call it non-Arrhenius reactions, in the sense that they can behave a little differently. So I'll try and give you a sense of what I mean by these pressure-dependent reactions. So one typical example is dissociation reactions, okay? The counterpart of which we're going to see later is called recombination. Essentially, the dissociation reaction is a reaction which globally, okay, can be thought of a molecule which splits up into its sort of constituents, okay? These happen all the time in combustion, okay? They're generally endothermic. I will illustrate what that means in a second. But essentially, what that means is that this process needs energy from the outside in order to occur. The reason why this should be is pretty obvious. You have a bond here between A and B, and you need energy to break it, okay? Into its constituents, okay? So you can think of a molecule of CO2 breaking up into a molecule of, for example, CO and some molecular oxygen. You can think of, for example, the dissociation of CH4, okay, into, for example, CH3 plus a radical of hydrogen, and so on and so forth. So whenever you have a molecule and you sort of break it up, you will have a dissociation. And dissociations usually happen when temperatures are really high, okay? So you can have dissociations, for example, in a combustion chamber in a rocket. You can have it less so in an aeronautical engine, where temperatures typically are lower, clearly, okay? Because they work with an excess of air, whereas in rockets you always have a sort of a stoichiometric or near one equivalence ratio. And being endothermic, generally speaking, they're also they have a negative effect on the overall frequency because they sort of absorb some energy, okay, from the system. But let's go and talk about the why they could be pressure dependent. Okay. Now, when I write something like this, okay, or something like this, okay, generally speaking, I'm not telling the whole truth. Okay, a dissociation usually occurs through a more complicated process. Oops. What's that process? Well, it's a process that involves a very important concept in chemical kinetics, which is called the third body. Okay, I will address this concept with the symbol N. Okay. What is a third body? Well, first of all, it's a molecule. Okay, it's a generic molecule, so it could be any molecule in the system, and it's a molecule that will participate in the reaction, but not chemically. So it will not change its chemical conformation, so it will not break its bonds or change its molecular structure, but only will take part in the reaction only energetically. Okay, so for example, AB plus M, okay, so there is a collision between AB and M of some kind, and M could be anything, I'll tell you what it is in a second, to form, well, the dissociated species A and B and M. So you see that nothing happened to M, okay? It only collided with AB. AB broke up, but M stayed more or less the same. We'll see that this is not even true. What is M? Well, M could be AB itself. It could be A, it could be B. It could be anything, okay, present in the chemical system that you were considering. Okay, and each of those will collide with AB, okay, with a different efficiency, okay? But apart from that, apart from the efficiency, okay, it's just a body that will not participate chemically in the reaction, okay? So it's just a means of collision, okay? So in fact, what you have here is not exactly the spontaneous breaking of a bond, okay? But it's really more of a collision with some sort of third body that does not participate chemically in the reaction, okay? Now, you may ask, but is this reaction that I just wrote down, is it an elementary reaction? Is it actually what's going on? And the truth is no, okay? This is still a global process. It's still a global representation of what's actually happening. So what is actually happening, okay, is a mechanism of the following elementary steps, okay? So the fact of the matter is that this is just a global representation of three processes, which are the following. So AB will collide, okay, with M, and I'll add an asterisk here to remind myself that this is a version of this molecule that is energetically excited. It was given, okay, more energy. So you can think of this as having more kinetic energy, or in some sense storing more energy through a jump in electronic orbitals. So it's just a way of saying this M has more energy, okay? Generally speaking, this is a reversible reaction between AB star and M. So you see, this mechanism here is just the transfer of energy from this molecule here to AB, okay? So AB collides with a very energetic third body, will inherit its energy, and M will essentially change from the excited version to the lower energy version. Why do we need this excited version? Because in fact, only when AB is in this excited form, it can actually, at this point, dissociate into A and B. Okay? Only this, not the AB. Okay? It will not, AB spontaneously will not be able to break the bond, okay, between A and B. But you may ask, okay, but who energized M? Well, in fact, this is we said it's an endothermic process. So really, M plus heat will give, in fact, the excited version of the third body M. So you see, this is an endothermic process because it needed heat from outside, okay? So that M can be energized, and you see now how it goes. It goes here, it can finally react with AB, transfer energy to it, and then the dissociation can happen. This third body will just pick up some more heat, will energize, and so on. You see that this is sort of a little machine. It's an elementary machine. It's composed of elementary steps, collisions that actually do take place, okay? So you see that this global reaction was actually hiding a lot of sub-processes that we were not at all we were not able to see, okay? That's why the global process is really a very rough, okay, summary of what's going on at the molecular level, okay? Now, why is it pressure dependent? Why is it so complicated? Remember that we started out from this sort of symbolic kind of step, okay? And looking at this, one may seem, okay, one may be entitled to say, okay, look, AB splits up into A and B, so this is a unimolecular process, okay? It involves one species. But remember, this is not exactly what's happening, so you can't really say that it's unimolecular in the sense that this is a wrong representation of an elementary step. This is not what's actually happening at the molecular level. Nor is this, okay? This is a global step, and you see that this involves two molecules, so you may think it's bimolecular. So is this process bimolecular or unimolecular? This is the question. I'll write it here. Well, the answer is that it will depend on pressure. And I'm going to give you the very short version of it, and then we will prove it mathematically when we actually construct a mathematical theory, okay, for these kinds of problems, okay? So look at the global problem, okay? The global problem told us that AB plus M, okay, was actually giving me the dissociated species plus M, right? So if I am to write down for this global process, okay, the rate of change of the molar concentration of A, which is equal to the rate of change of the molar concentration of B, this is essentially the rate constant, let's say K1, okay, times the product of the concentration of the third body and then AB, right? Now, let's think about what this concentration really is a second, because from the equation of state, okay, well, you see that if we divide by the volume, okay, the number of moles divided by the volume is exactly a molar concentration, right? So we can write down this is a molar concentration RT, right? And in fact, because P, the partial pressure is the mole fraction times the total pressure, okay? I can say that's NE over V RT, okay? And NI over V RT. And NI over V is, for example, the molar concentration of some species, MI, right? So you'll see that essentially, if I look at this reaction here, well, N, remember, does not take part in the reaction. So really, this concentration here is a function, not just of temperature. K1 will be a function of temperature because it's in an Arrhenius form. But if we consider this as being another rate constant, it will be a function of temperature and of pressure, okay? Because P is related, okay, to the molar concentration, okay? So this in general, so we can write it, for example, as K1 prime, okay, or K prime, doesn't matter, times AB, okay? Now, if we find out that in fact K is really a constant with pressure, okay, it's only a function of temperature, well then this global process, okay, behaves like a unimolecular process because you see this as a 1 here as an exponent. So we will prove with a theory that we're going to see later, okay, that in fact, okay, if we monitor the this rate constant here, at low temperatures, it will vary with pressure. It will increase with pressure. But then at very high pressures, it will plateau and it will stay constant. So this is when K prime is constant. You see that if K prime is constant with pressure, it only varies with temperature, then we're writing down an equation, okay, which is really behaving in a unimolecular way. Okay? On the other hand, if K at low pressures, if K is proportional to the concentration of M, this will increase with pressure, okay? Because as you increase pressure, the concentration of M will increase. And therefore, you see that now you can write down K prime, okay, as a constant times a molar concentration. So you see now you have an exponent here and an exponent here. The sum is 2, and therefore this is bimolecular. Okay? These are also called, well, they're pressure-dependent reactions. They're also called fall-off reactions simply because this behavior here at high pressure falls off. Okay? So this is another expression that is used. It falls off, okay, and it eventually plateaus to a constant. But I hope it's clear why at high pressures it behaves globally as a unimolecular level, unimolecular reaction, and at low pressures, in fact, as a bimolecular reaction. So it's pressure dependent, okay? We will prove this rigorously, okay, later on when we talk about, when we introduce a theory called the quasi-steady state assumption, okay, theory, which essentially, well, we're going to have to talk about more complex concepts such as time scales, okay? So I haven't proved anything, okay, in this particular case. I haven't proved why this falls off, okay, like this, and it behaves like this. But if it does, then you know that in the previous case, if K prime is proportional to the concentration of M, then you can write it like this. 1 plus 1 is 2, so this is bimolecular. If, on the other hand, it behaves like a constant with pressure, then you can write it like this, with this being a constant with pressure, and therefore you can write it only with one exponent, so it's essentially a unimolecular behavior. The same thing can be done for recombination reactions. Okay? So a recombination reaction is exactly the opposite that we saw before. Something like this. Okay? In fact, we already know that this is not what's really happening. Okay? There's going to be a third body involved. Okay? Which, again, does not participate energetically. Sorry, does not participate chemically with the reaction, but only energetically. Okay? You can hear me, right?
Yes, Professor. Yeah.
Okay. So this is the global process, okay? Which is hiding the following elementary steps. Okay, so you see that now you have two molecules, A and B, actually producing, so getting together, forming a bond here, okay, and forming a molecule of AB. Okay, so this is a recombination. However, this AB is in its excited state. So it actually needs a third body, okay, in order to form AB in its ground level, okay, and its actual final version here, AB. And clearly what happens in this process is that this extra energy has been essentially transferred to the third body. What the third body will then do when it's energized like this, okay, it will decay in its ground state, giving out heat. Okay, so you see it's exactly the opposite as before. And this, of course, now becomes an exothermic reaction, okay? It gives out heat. These are extremely important reactions in combustion because in the final stages of combustion, okay, combustion is essentially the breakup, okay, combustion. The kinetic aspects of combustion, let's say, is a breakup of the fuel, okay, into dissociated species, okay? So we have a dissociation process, okay, where the fuel breaks up into little pieces, which are essentially called intermediates or radicals, okay? But finally, they will have to essentially recombine to form the final products, which are water, H2O, water vapor, okay, and CO2 gas. And so you can think of the recombination step as the final step of your kinetic process of combustion, where reassociation processes are, recombination processes are actually responsible for the output of heat, okay, the exothermic part. But of course, to start the reaction, you need to split or to dissociate the fuel molecules, and therefore you will need an input of energy. So this is essentially why you have, for example, in internal combustion engines, you need a spark plug to initiate the combustion process. You need some energy input, okay? And then, of course, later on, through recombination reactions, you will have an enormous output of energy, okay? The net difference is clearly due to the fact that products are more stable, so they're in a lower energy level than your fuels, okay, than your reactants. Again, we will see this step by step, so it will become more and more clear as we go along. Again, here, look at the global process. If I need to write down the rate of production of AB, okay, this is essentially what? Well, some constant K, okay, here, times, well, what? The product of all the reactants, in this case, AB and the third body. But again, I can write down K prime, which is K times the third body, okay, plus A and B. So again, this process here can behave morally as bimolecular if K prime does not depend on pressure, okay? So K prime becomes constant with pressure, or if it is, okay, proportional to the concentration of M and therefore is pressure dependent, okay, it will be trimolecular, okay, because clearly you have essentially the sum of the exponents of the concentration is 1 plus 1 plus 1, okay? So again, be careful about certain processes, okay? Generally speaking, global processes, okay, which can behave, okay, differently depending on pressure. However, if you look at the elementary steps, okay, generally speaking, these all behave through Arrhenius chemistry, okay? So through the overall reaction rate expression that we actually know, okay? Let me just add an extra step. Well, no, I'll confuse you with this. So let me just let me just go on with chemical mechanisms, because I think this will be rather confusing if I eccezione. Salve eccezione. Sì, sì. Scusami. So let's take a look at what we call chemical mechanisms. So up until now, we have seen single elementary reactions, okay? Collision events between molecules, okay? Single collision events. But we've just seen that the elementary steps can form a more complex mechanism, okay? They can be, for example, telling a much more complex story. So you have a series of events, okay, that can happen in sort of in a cascade manner, and you have to consider all of the possible elementary processes that can happen. That's what we call chemical mechanisms. Chemical mechanisms can be very complex, okay? Starting from, I would say, maybe 40, 50 years ago, chemical kineticists have, so these are actually chemists, okay? They have dedicated whole careers on just finding out, given a chemical system composed of a fuel, an oxidizer, maybe CH4, oxygen and air, okay? What elementary steps actually can take place? What collision events can actually occur between all the molecules, and what molecules can be formed, okay? And you'll be surprised how many different chemical species can form from the dissociation of all the molecules that are present, okay, in your system. And just to give you an example, if you talk about the combustion of methane, which is the simplest hydrocarbon, so CH4, there are the simplest possible mechanism that exists today is composed of between 50 and 60 chemical species and roughly between 300 and 400 elementary reactions, okay? And this is, we're talking about just the simplest possible hydrocarbon fuel. So how many molecules can be formed? Well, not just CH4, O2, and nitrogen, but clearly all combinations. For example, we just saw that CH4 can dissociate into CH3, but also CH2, CH, even atomic carbon, okay? But not only that, they can also recombine to form more complex molecules, even more complex than the ones that we started with. Not just CH4, but you can actually, because clearly hydrocarbons and in general organic molecules are so versatile because of the presence of the carbon atom, you can actually form chains, okay? To the point that if you have enough carbon, for example, in rich mixtures, you can form aromatics, okay? Which are or even polycyclic aromatics, okay? So aromatics, if you remember, are closed chains molecules. And you can actually form eventually soot. So it's extremely, extremely complex. If you have nitrogen, okay, you can start the nitrogen chemistry, okay, from the dissociation of nitrogen. So nitrogen will dissociate into, for example, atomic nitrogen, and atomic nitrogen can react with oxygen to form nitrogen oxides, which are a form of pollution, okay? So you see how complex the situation can be and how more complex it is with respect to, if you remember, the chemical equilibrium problem, which was essentially a problem, an energetic problem, okay, of looking for a minimum of energy configuration, in that case Gibbs energy, given a number of species, okay? Now what we're actually doing is really figuring out what's actually happening and what everything that can potentially happen, okay, in a system, okay, non-equilibrium, okay, where you have molecules bumping and one another and the global composition actually changing in time, okay? So chemical mechanisms actually will describe all of that. So generally speaking, a chemical mechanism is composed of generic reversible, so elementary steps, reactions, which we formally always address as as we know, okay? Now you see that I'm also considering the reverse process now. So this is an elementary reaction. Remember, this is, when I use the word elementary, you have to remember that it's an actual collision, okay? So for this process, I can immediately write down the form, the Arrhenius form of the reaction rate. So we know that by definition, the reaction rate, okay, is 1 over the difference of the stoichiometry times the rate of change of the molar concentration, right? And you can apply this to all species, okay? Irrespective of, for all the species, so for all I's, okay? In general, because we've added the reverse process as well, okay, and this is what is new with respect to what we know, you can split this into a forward and a backward rate, okay? So that's what we say here. Well, that's what we mean with the subscript. So this would be the forward from left to right, and this would be the backward process from right to left, okay? So the overall reaction rate for this reaction will be the difference between the two. And we can actually write down for both of them the expression of the rate, okay? Which is what? Well, for the forward, it will be, so we will have a forward reaction, okay? Which is generally just a function of temperature, okay? Times the product of the species to the power of what? To the power of nu prime, okay? I. And I will go from whatever, from 1, generally speaking, to ns, okay? The reverse process is exactly the same with a different rate, in this case, kb, okay? Times the product of mi's to the power of the nu double prime, okay? So this is what the rate expression is actually is, okay? It's a forward rate minus a backward rate, okay? So from this, we can write down that the rate of change of any species, you can write down an ordinary differential equation, which is clearly a nonlinear differential equation of this kind. Okay? If you substitute then for omega this expression here. So you see, it's quite a complicated expression. It actually gets more complicated because in generally, we don't just have one step, but in the chemical kinetic mechanism, we have K equals, for example, 1, 2, up to NR steps, or elementary reactions, okay? Then we don't just have one expression like this, okay? So let me rewrite each elementary reaction in the following way, okay? I'm introducing essentially another index, not just I is for the species. So, okay, this is the summation on the species from 1 to ns, but also K. K indicates that this is the kth reaction. Okay? So we still have Mi here, because these are the species. And on the other hand, we have here on the right the same kind of thing. So you sum on all the species, 1 to ns for the kth reaction. Okay? And K, again, varies from 1 to nr. Okay? So, for example, if I have reaction number 2, I will substitute here for K2, okay? And I will write down my second reaction, okay? And so on. So in fact, overall, okay, if I am to write down the ordinary differential equation, so the rate of change of the molar concentration of a species, which is present in a more complex, okay, chemical kinetic mechanism, what I have to do is simply sum on all the reactions. Okay? And in each reaction, instead of writing this, okay, I will write ni ik double prime minus nu ik prime, okay, times omega k, okay? So we sum essentially on all the reaction. Clearly, omega k is the reaction rate of one of the individual steps, okay? So it will have this particular form, okay? So you see how complicated it is to build essentially the final form of the ordinary differential system of equations. But the bottom line is okay, that if we have a system, okay, a chemical system, so remember, I varies from 1 to an S, and K obviously from 1 to an R, okay, as in here. So this is the number of reactions, and this is the number of species, okay? And try to remember what I told you about the methane chemical mechanism, which was more than between 300 and 400 reactions. Here you have a summation of 300 terms, okay? But that's just for methane. Okay, if you look at more complex hydrocarbon molecules, then we're talking about thousands and thousands of reactions, even 10,000 reactions, and maybe 1,000 species. Okay, so you have a system of 1,000 ordinary differential equations. Okay, and the right-hand side will be composed of a sum of 10,000 terms. That's how complex it is. If you think of now putting also the fluid mechanics into this in a reactive flow, you can imagine how complex it is to actually solve the Navier-Stokes equations with this kinds of equations happening at the same time. Okay, so we're only getting started in terms of complexity. But if you want to make things a little bit more easy to handle, well, generally speaking, you can write down your system like this, okay? Where Y is essentially your vector, okay, of concentrations. For example, it could be, sorry, not X, it could be M1, M2, etc., up to MNS, okay? And this right-hand side term represents essentially, this is also a vector, represents essentially all of this term. So it's essentially a vector. It's actually the transpose. This is a column vector. And it's a column vector composed of each of those terms. So it's a very, very complicated systems of ODEs, okay? Ordinary differential equations. It's obviously highly nonlinear, okay? You can think of this as, for example, only, okay, an ordinary differential equation with these unknowns, so these dependent variables. You can think of also something where temperature can vary. If the temperature varies, for example, in adiabatic systems where you are not exchanging heat with the surroundings, okay, then you also have to add, generally speaking, a some sort of equation for the temperature. Okay, and you have to couple this conservation of energy equation with the conservation of species, okay, equation. So it's even more complex. And we're going to eventually write those down in the long form, okay? So it seems a little complicated at first, but really what you have to remember is Arrhenius, okay? And that is valid for all of the elementary reactions, okay? And then the fact that if you have more than one reaction, so if you have a series or a chemical mechanism, you have to sum on all of those reactions. Okay, you have to sum on all those reactions. But really, it's not more than that. Okay, to derive the rate of change of each molar composition, molar concentration. Whenever you have third bodies, okay, things may be a little bit more complicated because you may have this fall-off behavior, which is pressure dependent. But these are the overall information that you need to know, okay? So you need to remember. Global mechanisms are, in fact, an expression of, global reactions are an expression of elementary mechanisms composed of elementary reactions. Sometimes you have a third body, okay, in a reaction, and that will, which will not intervene chemically. And so you can think of that third body concentration as being pressure dependent. So sometimes it will be, sometimes it will not. We will prove why there are pressure dependent reactions later on more rigorously, okay? But if we are for a minute to forget the third body reactions, at this point, given any a mechanism of elementary steps, you can write down this system of ODEs, okay? So you can actually treat it computationally, okay? So you can write down, for example, a program in MATLAB which can solve this particular system of ODEs. And you will get into trouble if you do that. Why? Because I will just write it down here a second. This is one of the things that will be very important later on, because this ODEs are very stiff, okay? I talked about the concept of time scale. What stiff means is a very short term to say that when you have a temporal evolution, okay, of a global process that evolves in time, okay, well, this process can really be expressed as in terms of a large number of time scales, okay? And typically, in combustion, you have a wide range of time scales, from extremely short time scales to extremely long, okay? And when there is a difference between the shorter and the fastest time, the shorter time scale and the slowest time scale, the longest time scale, when there's a big difference, and by big difference I mean orders of magnitude, okay, differences. So from 10 to the minus 8 seconds all the way down to 1 second, so we're talking about 8 orders of magnitude different, then you use the word stiff, okay? And this is also a numerical issue, okay, to solve this ODEs, because if you use, well, if you've done some numerical analysis, you know that in order to solve numerically an ODE, you need a delta t, right? You need a time step, and this time step, if you use explicit algorithms, has to be of the order of the smallest time scale. So think about it. If you have 8 orders of magnitude between the fastest and the slowest time scale, in order to integrate your all slowest time scale, you need 10 to the 8, okay, small time steps. So you need to integrate for 10 to the 8 times, 10 to the 8 cycles. So we're going to tackle this problem as well, okay, the stiffness problem. And the reason why you have all these time scales, remember, is because each individual elementary reaction has its own rate constant, okay, and its own particular time scale, okay? So you can be a very fast reaction, but also a very slow reaction, okay? And again, I'm giving you all the spoilers here for later, okay? Another thing that you may be interested in is what's the relationship between what we've learned so far for chemical equilibrium and, for chemical kinetics and equilibrium, okay? So I'll say that again. What is the relationship between essentially the chemical kinetic concepts that we've learned and the actual equilibrium concept. So we're talking about a condition of equilibrium. Now, why do I bring back the equilibrium concept when I'm talking about non-equilibrium processes such as chemical kinetics? Well, if you remember, equilibrium or quasi-static processes could be considered as processes evolving in infinite time, right? And so essentially, at equilibrium, you can think of having evolved your system infinitely long until, okay, the final composition remains the same. Okay, so suppose that I have a process, a reaction. Again, I must have written this a million times by now. Okay, and if I write down my rate of change of the molar concentration of the ith species, what can I say about equilibrium? Well, at equilibrium, we know that we've reached an equilibrium point, right? So we've reached a state where the composition has reached its minimum of Gibbs energy, okay, and stays constant. It doesn't change at this particular pressure and temperature conditions, okay? So obviously the rate of change, okay, at an equilibrium point is equal to 0. I hope you agree, okay? If this is equal to 0, then it means that the composition, okay, has reached its equilibrium value. It does not change in time anymore, okay? So the rate of change is equal to 0, okay? And clearly, the rate of change can be written as the rate omega and then times the difference in stoichiometric coefficients, right? So what we're actually saying here is that the rate is equal to 0 at equilibrium. Now let's see if by imposing omega equals to 0, we actually have a coherent theory and we can recover some of the stuff that we saw for a chemical equilibrium. Okay, we're now very proficient in that. So remember how we can write omega, right? We just wrote it down, okay? We can have omega as the full, so always refer to this particular process here. Forward rate times the product of my concentrations to the power of nu prime minus the backward rate times the product, okay, of my concentration to the power nu double prime, okay? Now, if we impose this to be 0, I should also remember that I should add an equilibrium subscript here to remind myself that this is now the equilibrium concentration and does not change anymore. Okay? So we have now an expression relating the rates and the equilibrium composition. Okay? I can write down that the ratio, in fact, of the rates, if you take this on the other side, we divide by KB, is equal to the product here at the numerator of the products, so elevated to the double prime, divided by essentially the reactants, right? But if you remember, this was, if we, at equilibrium, okay, we were always equating this to the equilibrium constant in terms of molar concentration. Okay? This was our condition of equilibrium. So we derive this from chemical kinetics. And this is what we remember from equilibrium. Okay? So you notice now that there is, okay, a relationship in some sense between rate constants, so a chemical kinetic concept, forward divided by backward, and, okay, the equilibrium constant. Sorry, there's the equilibrium constant, which, remember, by definition, had an expression which, we'll recall it what it was, an expression which was depending on thermodynamic concepts, okay? Like, for example, the delta G0 concept, okay? So this is sort of the union step, okay, between a kinetic process which has been evolving for an infinite time and our equilibrium process. Let's delve into this a little bit more in detail. If you remember from chemical equilibrium, we were used to writing down the Kp, in fact, not the Kc. Kp was only a function of temperature, if you remember. This is the equilibrium constant. And by definition, we had defined this as the exponential, remember, of minus delta G0 divided by RT. This is what we learned in chemical equilibrium, okay? And you could write this as the reaction quotient at equilibrium, okay, which is the product of the partial pressures at equilibrium to the power of the difference of the stoichiometric coefficients, okay, for a given reaction, okay? Now, what I want to do now is relate essentially Kp to this Kc. How do we do this? Well, if you remember the expression for Pi, the partial pressures, let me write it here. So you have a molar. You have to learn a little bit how to shuffle the equation of state in different forms, okay? Otherwise, because it really exists in about 6 or 7 different forms, introducing partial pressures, total pressures, molar concentrations, and so on. So, sorry, I made a mistake here. So if you remember, the molar fraction times the total pressure is equal to the partial pressure, okay? And this was equal to the number of moles of species I divided by the volume times RT, okay? And this is essentially the molar concentration of the species I times RT, okay? We also wrote the molar concentration as Ci, okay, times RT. It's a little bit easier to write it like this, okay? So in fact, okay, the partial pressure, we can write it as the molar concentration Ci times RT, right? To the same exponent, okay? So, well, what about RT? Well, this is a constant, okay? It does not depend on I, so we can take it out. okay? Remembering that RT is to the power of this guy, so when I take it out of the product, I need to sum, okay, all the exponents. So you have, well, this is R. This is the universal gas constant times T. And then you have a product, okay? Okay? So if we call this Kc, okay, what we saw here, okay, I'm just writing essentially this notation as the CIs, and I'm taking essentially, you can see the compact form, okay? Then at equilibrium, we can write down a very simple statement that the ratio of the forward and the backward reaction rates, so this is a chemical kinetic concept, okay, can be related to the equilibrium quotient, or reaction quotient, we called it, which is, well, it's a Kp divided by this number here, this constant here, right? Kc is Kp divided by this. So Kp divided by RT to the power of the sum of Ni double prime minus Ni prime. Okay? Where again, Kp is a function of temperature and is equal to the exponential, of minus delta G0 over RT. Okay? So this is the relationship that we can write down between forward and the backward reaction rates, okay? To essentially the equilibrium constant, okay? Which is quite interesting if you think about it, okay? We have finally sort of brought together the two concepts, okay? We will eventually reuse this because clearly there is a concept of, if you remember at equilibrium, we had the concept of reaction being shifted more to the right or more to the left at equilibrium, okay? So this Kp, remember, was actually something that was essentially shifting between 0 and 1 and then bigger than 1 with respect to the fact that there was more shifted to the left and to the right. Now you can actually relate Kp to the ratio of the rate constants. How fast essentially is the forward process or effective, let's say, with respect to the backward process. And that clearly, at steady state, will eventually determine whether the reaction is more shifted to the right and to the left. So it actually makes sense that only at equilibrium, clearly, not before, but only when the reaction has reached sort of a dynamic equilibrium where the concentrations or the composition does not change anymore, it makes total sense to relate a concept of equilibrium such as the Kp, okay, the the equilibrium constant, with the forward and backward reaction rates, okay, or actually reaction constants more than rates, okay. I hope you intuitively you are actually seeing this, okay. So we are in a way visualizing the equilibrium now as a dynamic process where you have a forward process and a backward process which kind of balance out at equilibrium. in the sense that in favor maybe of products rather than reactants when the reaction is more shifted to the right, or vice versa, okay? And this kind of duality is this link between the equilibrium constant and the reaction constants, okay? So there is a link, okay? And we're going to be using it later on, so remember this, okay? Let me just go back one more time to the Arrhenius kinetics. So now I'm going back to full non-equilibrium processes, okay? So forget this link, okay? This link we had done, remember, only at equilibrium, okay? Maybe I should write this down. But far from equilibrium, we have a dynamic process of evolution where the composition changes all the time, okay? If you remember, we gave the example of an elementary reaction, AB giving C, and we had that the total collision frequency, you could write it down as a complex series of terms, essentially function of temperature, okay? I won't remind you what all these terms mean, okay? It's irrelevant at this point. And we have essentially regrouped this into a function Z of temperature times, okay, the product of the concentrations of A and B. So remember, this is an irreversible reaction. So the total collision frequency depends on how many molecules of A and B you have per unit volume, which is obvious, okay? So this is the molar concentration, and on the kinetic energy, okay? So on temperature in this complex kind of form coming from collision theory or kinetic theory of gases, okay? Remember that what we said is that the temperature has can have a distribution, like a Gaussian distribution, like this. This would be sort of an average temperature, and you will have very small molecules having very little kinetic energy, and very small number of molecules having very large kinetic energy. Okay. Now, this is the total collision frequency, but we said that only effective collisions, okay, collisions that have an energy, okay, which is larger than what we called an activation energy, will end up actually reacting through this process, A plus B giving C, okay? Only those that have energies which is larger than a threshold energy. So how do you find this fraction? Well, simply you integrate the probability distribution function, okay? So essentially you integrate between 0 and a certain temperature, okay? And eventually what you have is the so-called cumulative distribution function, okay? So again, this is T. So this is a function, essentially, it's a very easy concept. It goes from 0 to 1, okay? Because remember, the integral between 0 and infinite, okay, of this function here, which we can call PT, the probability distribution of T in dt, is 1, okay? By definition of probability density function. The integral between 0 and t, okay, is this function here. What this means is essentially as you increase the temperature, you have a larger and larger fraction of molecules, okay, having an energy which is bigger than a certain activation energy. So this function here is, in fact, analytically, you can prove this, but I'm not going to do it, e to the minus EA over RT. Okay? And clearly for t going to infinity, this goes to 1, essentially. Okay? Depending on whether EA is bigger or smaller, you can have, obviously, different shapes, okay, like these, okay? But what, in effect, this is the fraction of molecules having energy bigger than an activation energy. So, in fact, the Arrhenius form of the rate of reaction is essentially the total reaction rate, okay, Z times A times B, but mitigated by the fraction of molecules having enough energy, okay? So when I ask you, why does the reaction rate in the Arrhenius form have this particular form? Okay, the answer would be, well, it has this particular form because the pre-exponential factor, this is what this is called, just simply because it's written before the exponential. Okay, Z times the product of the molar concentrations will give me the total frequency, okay, of collision between the molecules present in my system. Okay, but then clearly out of this total frequency, I only have to take a fraction of those molecules that have enough energy in order for the reaction to actually take place. Okay, so you see now that essentially we have a final form for our reaction constant KT. Okay, the reaction constant KT will be a pre-exponential factor, which I wrote earlier, times its exponential. Okay, so that's our K. Okay, we've always kind of written it in short form, but in fact, this is what it has in terms of the dependence on temperature. Okay. And it's essentially, generally speaking, only a function of temperature, unless clearly you are considering third bodies, then it's a little bit more complicated. There will be a pressure effect as well. But I mean, forget the third bodies for a minute. This will be your reaction constant, okay, times clearly your product of concentration. So this is how omega is expressed, okay? Now, how can I write this pre-exponential factor, Z? Remember, it was a series of, there was a square root and something like that. But in fact, you can write down in very compact form Z as some constant, depending clearly on the particular reaction, times temperature to the power of alpha. Okay? So if we write this, so to be perfectly clear, if we go up here, that's why I'm writing Z in this form, okay? It's some constant times T to the power. So generally speaking, in this case, it will be 1/2 alpha. But the chemical kineticist will tell us exactly what this alpha will be. And so, in fact, omega will be the pre-exponential factor Z, which is B T to the alpha, times the exponential, okay, of the activation energy divided by RT times whatever product of concentrations we have. Why am I writing this way? Because you see now that given a reaction, actually an elementary reaction, the rate is actually uniquely determined by three constants. B, which is this constant here, the temperature exponent, so this is B, the temperature exponent alpha, and the activation energy. I don't need anything else, okay, to be specified. Because if you give me B alpha and EA, I can always write now the form of the reaction rate. Why? Well, because the temperature here is the temperature, RT, R is the universal gas constant, and A and B is the term, well, whatever you have here, this is the product of the concentrations, right? To the power of whatever. So generally speaking, D double prime, D prime. So this is determined directly from the stoichiometry of the reaction, which is fine. So that's why chemical mechanisms usually are given like a list of reactions. I actually will show you one maybe tomorrow, a list of elementary reactions, and then 3 columns, okay, giving you B, alpha, and the activation energy, okay? Let me just visualize the reaction for 1 minute, because I want to go back to, in this last 2 minutes, to a diagram, okay, that we have been used to, which was in some sense a function of the progress variable, okay, of a reaction, remember? And suppose that I'm considering, for example, the reaction AB giving C plus D, something like that, okay? So if you remember now, we were starting from A and B, okay? And this was, in some sense, an energy level, okay? So this is for example, a measure of the enthalpy of formation, it could be, of A and B. And then you had, at the end, C plus B, right? Sorry, C plus D as your product, which is in another sort of different energy level. Now, essentially, I can visualize the process energetically as something like this, okay? This is a sort of a schematic representation. Why do I have a bump here? Well, because in fact, in order for A and B to react, okay, they need to collide with enough energy so that they can overcome exactly this activation energy EA, okay? So visualize this as the reactants. You have to give enough energy for them to collide sort of with enough energy, again, to form, in fact, what we call an activated complex. This is a symbolic form, meaning that says that essentially A and B, sorry, A plus, sorry, I made a mistake here, going too fast because I saw the 2 minutes. You should stop me when you think there's something wrong. This was A plus B, clearly, okay? A plus B giving C plus D, okay? This is A plus B, okay? Will form a so-called activated complex. It just means essentially that AB will collide energetically enough so that they will penetrate into one another, okay? Reshuffle their bonds in order to finally form C plus D. Okay? So this is what you have to understand, what you have to visualize as this bump, as the meaning of this bump. Okay? Now, clearly, at the end, the net effect, the net difference, okay, between the reactants and the products in terms of energy will be a heat of reaction. So, for example, in this case, it's negative because it's the products minus the reactants, so it's negative, so it's an exothermic process. Okay? But you can also have an endothermic process where you start from A plus B, but now your final products will be higher. Okay, so you still have an activation energy, which you need in order to bring together A and B in a collision, which is energetic enough, but then the net effect here will be a positive rate of heat of reaction, which means that the reaction is endothermic. Okay, and this kind of concludes the picture that we've had seen also in a chemical equilibrium, and now we can also link a very sort of kinetic non-equilibrium concept such as the activation energy. And in combustion, it turns out that this hump, this mountain that you have to climb on before the ball can kind of roll down energetically towards a lower level, is pretty stiff. It's pretty steep, okay? And we'll see what that means for reactions. But I'll anticipate that the reason why combustion processes can have very, very fast timescales is because the activation energy is so high. Okay, sorry that I used up a little bit more time. You can still hear me, hopefully, right?
Sí, profesora.
Okay.